that we have solved the wave equation on an interval, we want to change it into an infinite string. So we are imagining it that the string we're plucking is infinitely long. That is represented by the fact that x doesn't belong anymore to an interval from 0 to L, but x is in R. We have the same Laplace equation as before, wave equation as before, and we have the same initial conditions on y and on yt. And we're looking at a physical problem, so we are assuming that our oscillations are bounded at infinity. So instead of using the separation of variables, what we're using instead is a Fourier transform with respect to x. Now, I will not give you the solution, but I want you to think a little bit, why are we not using a Fourier transform with respect to t? Why did we choose x? Anyway, we're going to work with a Fourier transform with respect to x. So we're introducing y hat, that is the Fourier transform of y with respect to x. So it's an infinite integral from minus infinity to plus infinity of y, that is a function of x and t, times the exponential of minus I k x. You see, x there is where we choose which of the two variables of y is the one we're taking a Fourier transform with respect to, dx. The inverse Fourier transform is very similar, as we have seen. So it's the way we can go back from y hat to y. We have y being 1 over 2 pi, infinite integral from minus infinity to plus infinity, as y hat, this time is a function of k and t, times the exponential of I k x dk. If we take the wave equation, so c squared yxx equals ytt, and we apply the Fourier transform to it, the Fourier transform with respect to x, so the second derivative with respect to x of y, through the Fourier transform, gains a factor of ik squared in front of y hat, while the second derivative with respect to time of y is the second derivative with respect to time of y hat through the Fourier transform. So we retrieve a problem that is y hat, second derivative with respect to time, plus c squared k squared y hat equal to 0, where y hat is a function of k and t, where k is anywhere in the real axis and t is positive. What are the initial conditions on this? Well, for y hat k for t equal to 0 is the Fourier transform of y x for t equal to 0, and we can replace y x comma 0 by f of x by the initial conditions of our initial problem. So this is the Fourier transform of f hat, the Fourier transform of f that we denote by f hat. This is a function of k. We do the same for the second boundary condition, so y hat t is equal to the Fourier transform of g. So we have the second derivative with respect to time of y being something that depends on k times y hat. If we think of k as just some constant, we can solve this by saying that y hat, function of k and t, is a sum of cosine of ct and sine ct. Now we have to figure out the values of the in front of this. So we need to find a and b. Or we can rewrite it as a complex exponential. We have c times exponential of minus I ct plus d times e and I ct. For t equal to 0, we have that y hat computed at k t equal to 0 is c plus d, and from the initial conditions that we have, this is equal to f hat k. That means that we need c being a function of k and d being a function of k. In the same way, we can write it as the derivative with respect to time is computed at t equal to 0 is minus ICK times capital CK plus ICK times capital DK. And this needs to be equal to G hat K. Maybe it's actually easier to look at it from the sine and cosine perspective, because when we take y hat computed at time equal to 0, we only have a equal to f hat k. That means that a needs to be a function of k, but we also mean that we know ak perfectly. Ak is equal to f hat k. In the same way, if we take the second initial condition, y hat t at k comma t equal to 0 simplifies away to be bk times c times k. And this needs to be equal to g hat. So we can write y hat as g hat function of k times cosine of ckt plus g hat divided ck times sine ckt. And now we have to do the inverse Fourier transform. So we know that y is equal to the inverse Fourier transform of y hat. So it's 1 over 2 pi of the integral from minus infinity to plus infinity of y hat exponential of ikx dk. And this, we can at least write it in closed form. It's not necessarily easy to compute, possibly not even possible to compute, but we have a way to determine y for any value of x and t.